il y a le micro pour YouTube aussi. Sur YouTube. Ah, il faut...
Ah, c'est bon. Donc, on va écouter l'exposé de Daniel sur machine learning et système dynamique. C'était ses travaux de thèse. Et les jurys est composé, il y a deux rapporteurs. Quelqu'un qui est à distance, c'est Madame Alessandra Lanotte, qui est en Italie, et Monsieur Chosseran, qui est là-bas, je ne sais pas si vous le connaissez. Et puis le reste des jurys, il est composé par Lionel Matelam, Alexandre Alocène, et le directeur de thèse, qui c'est Sergio Kibaro, encore un ancien du labo. Voilà, et puis moi-même, José Maria Fulana, je suis dessiné président du jury. Donc Daniel, il y a 45 minutes, je c'est ton travaux.
Merci. Okay, so I'm going to discuss in English. So thank you everyone for being here, my soutenance. The title of my thesis is Machine Learning for Dynamical System Modeling. Now I'm going to start. The title is about dynamical system modeling. Now we focused more our research on a complex dynamical system. How can we define a complex system? There is no universally accepted definition of what a complex system is, but we can say that every complex system has this property, like the non-linearity and high sensitivity to initial condition. We show the picture of the Lorenz attractor, the Lorenz model, is a 3D trajectory. And in the right picture, we have two different trajectories of the Lorenz model. We can see that they begin in the same, the two trajectory begins really close, they're really close at the beginning, but after a period of time, these two trajectories start to diverge. And this is one of the key issues of a complex system, which is the high sensitivity to initial condition. We focus our interest in turbulence. So we were more interested in this type of physics because it's really relevant. Turbulence is a complex system for definition. Historically, Leonardo da Vinci was among the first to discover turbulence, or at least to understand it is important to study the fluids in turbulent motion. And here we present one of his illustrations in Milano, which is an illustration of a fluid that flows out of an aperture with turbulent behavior. The range of application of turbulence now in the modern times goes from engineering, so airplanes, cars, to weather forecast. In the left picture, what we have is an airplane passing through a crow's smoke. In the right picture, we have a satellite photo of the US West Coast by NASA. Especially in the weather forecast, there is also an important property of turbulence, which is the multi-scale behavior. So it means that a turbulent system should be studied at different scales, from kilometer scales, so like in the weather forecast, to the smallest scale. And this is something really interesting, and this is key in all the turbulence systems. Here we have the equation, the Navier-Stokes equation, the very famous Navier-Stokes equation, that are nonlinear, complex, and so that's why they are important, because they describe turbulence. So we have the velocity field, and then we have parameters. So these are the adimensional Navier-Stokes. This parameter is called the Reynolds number, which is an important value that classifies the flux, classifies the turbulent flow. And if this number exceeds the Reynolds, the critical value, the fluid starts to be turbulent. So for this reason, it is more difficult to study turbulence by the point of view of the different trajectories of the fluid. So we can focus our attention on statistical quantities like this one, which is the energy. And the Kolmogorov law states that whenever we are in the inertial range, the energy that we can write in this form in Fourier space follows a power law, which is really famous. As we can see here, we have in turbulent system, normally we have energy, which is injected at higher scale, larger scale, like K in. And then we have a flux of a characteristic slope, which is exactly a Kolmogorov law. And then we have the dissipation in K out. So we see in the picture that we have just a scheme of the energy spectrum of a turbulent system. We talked about the multi-scale properties of turbulence, but how can we measure this important property of turbulence? So what we can do is to introduce the structural function. As we can see, this function is a mean, is average on time of the velocity field in the position x times r minus x, minus the field evaluated in x to the power of p, which is linked with high-order statistical moments of the distribution of the velocity as a function of r. And we can see that there is an equivalent of the Kolmogorov law, is basically the behavior of the structural function is a power law with function, with this CDP. And this function is really non-trivial at all. As we can see in the plot that we have on our right, what we see is that we have the anomalous scaling exponent CDP and P, and the line, the gray line, is the Kolmogorov law. The points are experimental data that deviates from the Kolmogorov law. So to exactly predict this behavior is also the key of the theory of turbulence, because this is not at all a trivial behavior. And so, like for example, here we show the prediction of the multifractal models. I don't want to go too much into this, but just to show this important feature of turbulence. What we can say is that, practically speaking, turbulence is ruled by Navier-Stokes equation. Are really complex to simulate. They require a huge amount of time. Also for the problem of multi-scale. We can see that there are different possible solutions to mitigate the issue of the direct numerical simulation. One of these is reduced order model or large eddy simulation, for example, in the context of turbulence. Then we can try to apply machine learning, which is what we aim to do. And then what we did at the end, what we're working on now, is to apply machine learning to improve reduced order models. Now, I just would like to give you basics idea about the context of the theory of machine learning, because it's important to know. So many problems start with the dataset D, which is a collection of vectors. We have the input x and the output y. The idea is that the model should be the model which is a function f from x to y with a certain set of parameters. the loss function is able to say how well the model performs on the observation. So the key point of the model is to be able to reproduce the right data. So we measure the performance based on the loss, also during the training process. The training process is really crucial, is really important in the theory of machine learning, because it's exactly the algorithm, exactly the way in which we find practically the set of parameters that minimize the loss that we want to minimize. The most common used, the most widely used loss is the L2 norm, is the one in the formula. That's also the one that we used. And x hat is the prediction of the model, while x is the training set, the training data. Historically and also technically, it's important to at least describe the multi-layer perceptron, because it's one of the most important models, one of the most widely used models in machine learning. And so what we have here is just a scheme of the multi-layer perceptron, which is an evolution of the perceptron of Rosenblatt, which is just one neuron. So the perceptron was a mathematical model of a neuron. So the idea is that the model is characterized by weights, so there are data, links, and nodes that came from the input to the output, and then the activation functions. Each neuron has an activation function, which is nonlinear, and this is why it is important to know also that the multi-layer perceptron is nonlinear, because of its capability to approximate any function f, x, theta. And there is also a theorem, universal approximation theorem, and that's why they're very important, that with more than one hidden layer, this type of models, with a known number of nodes, are able to predict with arbitrary precision every function f of x. So that's why they're really interesting also. And here there's just a scheme of a multi-layer perceptron with two hidden layers. Now it's more important also to discuss about the machine learning for dynamical systems. The idea is that we want to learn, we want to apprehend dynamical systems. So the best models, the best machine learning models are the recurrent neural networks. So we can also use the multi-layer perceptron, but it's not the best. And why it is not the best? What we have here is the general function of a discretized dynamical system, which is x at time t plus 1 is a function of x at time t, so we are with an initial condition. And in a certain way, a recurrent neural network could be seen as a dynamical system itself, because h dt is the hidden state, which could be physically interpreted as a memory, and this one is updated every time step. It is a function of h dt and x dt. So as we can see also in the scheme that we have on the right, what happened is that here there is an illustration of a cell of a recurrent neural network. In input, it takes the memory at time t minus 1, or the hidden state. The input x at time t. Then it gives as output as a function f, which is normally in common use the hyperbolic tangent. It gives an output as a function of memory and the input. So what we have here is that the prediction is a function of x and a certain memory that the model has. And this is just one-step memory. And because of this, if we start to apply this type of architecture to solve more complex problems, what happens is that then the model starts to rely too much on memory, and so it's not a lot capable to apprehend long sequences, for example. So that's a bit the idea. And that's why also this type of model have this problem that was solved by the more famous long short-term memory, which is a quite complete architecture, but we're going to have a brief look inside. So what we have is the most important difference with the simple RNN, recurrent neural network, is that here we have a memory, CT, which is a cell state. It is able to propagate memory in time, and the model is able to direct modify the memory. And how this mechanism works? With the gating mechanism. So the gating is really crucial in the LSTM, because what we have here is, for example, we have the input gate that controls the new information that are sent to the memory, this part. And then we have the forget gate. So the forget gate and the input gate works in a kind of opposite way, in which we have the input that give more importance to a point in the system, in the training set, while the forget gate is able to erase in a certain way the memory. So the model is not doesn't rely too much on the memory, but is able to control the memory. So that's a real important difference. Indeed, these models, well, they perform very well on predicting time series. Now, what we want to show now is a first approach of a complex system that we followed. So we start with a system which is well known to be complex, but it's also relatively easy to simulate, that we know very well, we know everything. And so we can focus more on the results on the machine learning part, since we already know very well the physical model. Normally, the problem with machine learning is to find the right amount of data to train a model. Because we talk about the training set, but there is no really a theory that is valid for every complex system that is able to give the right definition of the quantity of data that we need to train a model. And when we approach this problem using dynamical system, we can also use the theory of dynamical system to understand better the right quantity of data that we want to use for the training, because there are theorems and the theory is well known, and that's why we use dynamical system. And what we want to do also, we aim to find, to leverage the information that we physically know about the system into the training process, for example, or to use it to improve the training. And that's basically the idea. So here I just wanted to do a little bit of history on the Lorenz model. What we have is the Lorenz model. That was one of the first simplified model of convection, atmospheric convection. And here there are the equations that define it. The equations are nonlinear, and with a certain choice of parameters, the system is chaotic. That's why it is really interesting to study. So what we wanted to use for training the Lorenz model was to apply a curriculum learning strategy, which means, like a human, for example, learns a language. A human starts by learning something that is easy, and then it moves towards complex things. So in a certain way, we try to follow this idea, and we use the entropy as a measure of complexity to improve training. What has been shown in an article that our team published. There is just a picture that I want to show, which is really interesting to me. And we have in these two figures, we have the red one, which is the true trajectory. The blue one is the prediction. What we have is the differences between the same architecture trained only on two different datasets. So the only difference between these two is the training set. So we can find the first one, which is trained from trajectory sampled randomly on the attractor. We find that after a few Lyapunov time, the predictions start to diverge from the real one. And in the second one, what we find out is that the prediction is really improved. So we can find, also we can go further in the prediction with the same architecture, but trained only on different datasets. And these are datasets from fixed point trajectory. So that there are trajectory close to the fixed point. I'm going to explain a bit more. What we have is to try to explain these results. We studied two different datasets from the Lorenz model. And the one in the left is from a fixed point, so there are trajectories nearest to the fixed point. And then we have trajectories sampled randomly across the attractor. That's the definition. These are just two samples of a subset of trajectories that I wanted to show that they has been used to train the model. I just want to give a brief definition of SVD entropy. So we have a time series X. We use an embedding of with the time tau. We create a matrix M. Then we apply the singular value decomposition of M, which is well known, and we found the singular value. And that's the entropy in a Shannon way of the singular value decomposition of M, which means that measuring the SVD entropy in these two subsets would be interesting to understand which one is the best to train a Lorenz model with a curriculum learning strategy. In the left picture, we show an histogram of the SVD entropy of 100 different trajectories for each type of dataset. As we can clearly see, there is a huge difference between the two datasets, and the fixed point is the one that is less that has less entropy. And we can see something also in parallel in the right plot. Then we find the average SVD entropy always over 100 trajectory, but as a function of number of points. You see at the beginning the fixed point dataset is growing, and after 200 points, what we can see is that the fixed points start to be less with less entropy. So we can just have a summary of what we found out. We were able to see with the Lorenz model that there was an improvement in performance through curriculum learning, and what we saw also was that applied the SVD entropy to explain it. We also work on a Fisher matrix analysis that I'm not going to show now because we don't have too much time. But also that one is be interesting to see. After these results on the Lorenz model, we start to use a different system, different class of systems that are more complex and are also physically more interesting. Because the Lorenz model is very well known, while the shell model of turbulence, which are the discretized model of turbulence, are really interesting for many reasons that we're going to show. The idea to create this model is to start from Navier-Stokes in Fourier space and discretize it. So we want to discretize the Fourier space, and we have the isotropic hypothesis, in which the UN, the modes, are just a function of t, and they are complex. This is just analogy. That's just an analogy to show where these models are from, but then they have their own life, in a sense that we can discretize the Fourier space, we divide it in shells, and we can create an equation for this shell that can interact with the two nearest neighbor. Gn is a function of order 2 nonlinear of the UN. And this is really similar to the equation of Navier-Stokes. It is in a different place. So this is a set of equations of ODE. That's just a sketch of the phase space. I just want to figure out why it is called the shell models, because this gray shell is the part that is allowed to be is the only part allowed in the system. In the phase space. That's just to show a visualization of it. What we have in this system is interesting because we have the conservation of energy. If we wrote the energy, we can see that it's constant. Without dissipation, without viscosity. It is also possible to find again the Kolmogorov law. If we define the spectral density energy in this way, as just the mean of the module of the UN squared, what we find out is that in the inertial range we still find out the Kolmogorov law, which is a really interesting analogy with Navier-Stokes. But the best analogy is also the fact that we can define the structure function, and we can also find the anomalous scaling exponents that are, as we can see in the picture, are really close to the real one in Navier-Stokes. So that's why the shell models are really important, because even if they mathematically speaking, they're simple because they're just ODE. They're more interesting because they show statistical behavior, which is interesting and which is really close to the one in Navier-Stokes. So we can find here the difference between the simulation of the Sabra model and the shell-Lévesque. That's just to give the idea that these values are really close to the real one in Navier-Stokes. So what we wanted to do, I just want to explain why we developed a new algorithm on LSTM on shell models, and to understand it's useful to understand how the standard training of a RNN happens. So at each time step, the prediction x at t+1 is a function of xt htt. So that's the idea. What we want to have here is I want to focus the fact that we only use training points to predict the next one. Use a scheme of a standard training, for example. So what we do is learn to predict one point from the one in the training set. each time the model is trying to reproduce these points. And then we compute the loss between the two sets, between the training set and the predictions. What happens is that if we want to exactly simulate a dynamical system, this is not exactly what we want to know, because this type of training struggles to handle the propagation of errors in time. Why? There is a huge difference between what we do for generate point and what we do for training the model. When we want to generate point, we start from an initial condition, x0, and then we start to generate points only with predictions, because the model is able to use its own points to generate the trajectory. While during the training set, during the training, what we say to the model is to use the training point to predict the next one. But in the reality, we want a model to be able to produce its own point. Given an x0, the model needs to know how to predict x1, x2, starting from x0. And especially in dynamical system, in complex system, it's really relevant to know that there is a huge difference, because a small error at the beginning is would be really bigger after the training. So that's why it is really crucial to let the model understand its own error when you have to generate points. So for example, what we have, I don't want to enter into the training details, I just want to show the idea more on trajectories. So these are just trajectories of a Sabra model. But just to let you understand what is really the difference between these two. So the red line is the trajectory generated by the LSTM on its own. So at the beginning, what it happened is that the LSTM start to update the memory. After the blue point, there is a split in the trajectories. So what happened is that the blue model is the one-step prediction, which means exactly like it was trained for. So you give a point and then predicts the next one. Then you give the next true point and then predicts the next one. But what did happen here is that the model is well trained to do this operation of one-step prediction. And as soon as we ask the model to generate its own points and its own trajectory, like a real dynamical system, it starts to fail completely. So that's interesting. This is just what I wanted to say. Here we have a more complex trajectory, because also shell models is very multi-scale. So the model should be able to reproduce a large scale of behavior, also in trajectories. And in this way, it fails, at least in the trajectories. And what we wanted to do more in details is to develop a new algorithm. Given a training set of UN with n shells that are numerical solution simulation to the Sabra model. We have 10,000 data points per shell. They're just the length of the trajectory. We want to develop a new algorithm that is able to mix these two approaches, the approach of training and generating points. At least you have to consider this approach. So here we have the equation of the training. We have U. What we have is that we can split into the training algorithm. The key point is that for 0 to h, the model only updates the memory. So it works like the standard training. and after it starts by using its own generated points. Here there is a scheme, because I just want to be a bit more clear on this. So we can split into this diagram. In the left part, we have a representation of a standard training, which means we have data x1, x2, xh, and then the model reproduces the next step, x2, x hat 2, x3 hat, and so on, until it reaches h, which means that in this model, the only things that change is the memory inside the LSTM cells. After h, here there is the key part, the crucial part in the algorithm, which is that the model is true, it produces a new output in the pointer's trajectory, but it also uses it as input to generate new points. So from here, it starts to generate model without knowing the real points. We know the real points, and we use it as to minimize the loss. So after, we can evaluate the loss between the real point. And we train the model only on these points. You evaluate the loss only on these points. Now, I'd like to show you some results that we obtained by applying this strategy. On the left, we have the spectrum of the model, which has been trained for the case of N12 shell, okay, but for the two learning algorithms. As we can see, the orange one is really closer to the real spectrum than the blue one. The blue one is the standard training. So we can see that in the spectrum we have this behavior. Then the spectrum is not enough to characterize the turbulence, so we focused also on the anomalous scaling exponent. And what we found out was that the error, the relative error of the critical exponent, is really better in the forecast training model than in the standard one. So that's the interesting part. We tried with different type of dataset with n equal to 12 or also to 19, and we obtained the same results. That's the idea. Here we also have two function of the critical exponents, and as we can see, the only thing that changes here is the number of shell, but we still have the same results. The standard deviation is a bit higher in forecast training, but the mean is closer to the real value. We can find it. When I say the real value is the one that we evaluated with the Sabra model that we used in the training set, so the one that used in the training set. And this is interesting because our model doesn't use a huge amount of data. It just only uses a relatively small quantity of data to obtain these results. So what we can do a small summary on this part. So we used the Sabra model, which is a model of the group of the shell models, which is a simplified model derived from Navier-Stokes equation. It preserves the key properties like anomalous scaling exponents that are crucial in the multi-scale properties of turbulence. We show how the standard training from an idea of a paper of Benjo is not exactly the best way to train a model on, especially on a complex system, especially on a complex chaotic dynamical system. We developed a new algorithm, which we call it the forecast training, that combine training and generation inside the training algorithm. And then we show that we improved actually the results with this new forecast training. And this could be also seen as something like a benchmark of future work, for example, to apply the same ideas on other systems that are more complicated. Then we start to work on the CD-ROM model. Now, what is this correct deep ROM models? Actually, is to, as we already said, was to improve with machine learning standard reduced order models. To do this, we took the idea, the real model was published by one colleague of Jose in our group, but I just would like to give an idea of how the model works. We have we took the idea of large eddy simulation, in which we have U, a field which is filtered, and in which we separate the large eddies from small eddies, while the LS is able to capture large-scale turbulent structure, and then it starts to modelize the small scale. So we divide the scales. So the shell models are really interesting because they basically they are created to exploit the properties of multi-scale. What we normally do is we have a model, a Sabra model of n equation, and we would like to reduce the model with m equation. So in the same idea of large eddy simulation, we applied it to the shell models, and we would like to try to see if there is a way to improve performances on a reduced order model, adding also the machine learning part, following this idea in the system. So normally, what we have in general, or to be more general with this model, is we have a dynamical system, and we apply a method of dimensional reduction. So we can call it U tilde of t, and the matrix, which came from a kind of projector operation. But for now, we're not really interested on this, because normally in machine learning is known as PCA, because it's a method of reduced dimensionality. But we're not really concerned in this, because, as we said, we just would like to know to cut the shells like in the LS approach. And the key point is to find a correct dimension of this space that is able to reproduce it. And this is just with PCA or dimensional reduction. But this theory is a bit general, with different method of dimensional reduction. And what we can find is that normally, if we have a reduced order model, we only stop to this part. So we can write the time evolution of our model as a function of the reduced model by doing an approximation. So we say that this term we put it to 0, we neglect this term. What we want to know, what we want to do instead, was to avoid to just eliminate this term, and we want to modelize it into a function as a function of a memory. This term y is the memory. We can call it the memory of the neural networks. But the idea at the end is that we modelize with machine learning, so with neural networks. So E in ADT and the residual term are neural networks. This is what we have. Lambda is a bit technical details, but this is the system that we want to have at the end. So instead of just the reduced order model, reduced order model stands for the system that we have here, basically. We instead of neglecting this term, we try to modelize it with machine learning. Here, for example, there is just to be a bit more clear on what we do by cutting shells. What we do on a reduced order model is that we cut. The idea was at least to cut the last shell. And here we have a picture, a plot of a reduced model, and with this model should be able to reproduce the same statistic of the entire model. But we can choose how many shells do we cut, because the model is perfect, is made for it technically. And so what we did was to use a Sabra model of n equals to 19, and then we try to apply the CD-ROM model to evaluate anomalous exponents. So here we have the spectrum of energy for a reduced order model of Sabra. That's what we have. After the training, we had some preliminary results, even if we had some something that we're not so sure about, so which is about the loss during the training process of these models. But the preliminary results that we obtain are encouraging, because we have the CD-ROM, which performs very well compared to the ROM model. This is actually a mean CD-ROM of 10 independent realization of models. The crucial part was also that the training time was quite long. That's why we only have 10 models, but it's something that we should work on. And what we have here is that we can see also by looking at the plot, we can see that the error is really lower for the case of CD-ROM. These are just preliminary results, but these show that there is at least a possibility to improve reduced order models also on complex systems like the shell models of turbulence. As a conclusion, we can say that we study the possibility to use physics-informed training set with curriculum learning strategy. We investigated the application of machine learning for complex dynamical system. We begin with Lorenz system, which is the benchmark of complex system. Then we moved to shell model of turbulence, which are more physically, they are more interesting, relevant. And we developed a new training algorithm that fits better for shell models, but it's the idea are general. And then we explored the possibility to improve reduced order models with the machine learning. And as future work, we can think to apply the idea of forecast training to more complex systems, finish the results and the idea on CD-ROM applied to shell models, and then maybe move to more complex systems like 2D or 3D turbulence. So that was my last slide. So thank you.
Thank you very much, Daniel. Time was perfect. Thank you very much. Timing was perfect.
Ah, okay.
I wait for the classical. Oh, okay.